about how weak acids, and weak bases for that matter, don't completely ionize in solution, meaning they don't completely dissociate into products. Okay. So an example that we have was acetic acid in water, and it forms its conjugate base, which is the acetate ion, as well as the hydronium ion, which is the conjugate acid. Okay. One thing that then we talked about is the strength of different acids. You can refer back to the chart with the arrows to look at different strengths of acids. And I'd mentioned that acetic acid doesn't dissociate very much. If you put 0.1 molar acetic acid in solution, only about 1% of that acetic acid will dissociate into the conjugate base, acetate ion. So here's another table that's in your textbook that shows a list of weak acids and their Ka values. All right, so here's our acids by name, their formulas. Also shows the conjugate bases, and then different Kas. Okay? And as you recall, the larger the Ka, the more products are formed. And you're going to find that our Kas and Kbs, for that matter, when we think about weak bases, they're all going to be less than 1, meaning the reaction itself is reactant favored, but still the larger the Ka, the more products are formed. So, according to this list, chlorous acid would be the strongest acid with a Ka of 1 times 10 to the minus 2. And phenol, which is the bottom here, would be our weakest acid with a Ka of 1.3 times 10 to the minus 7. You don't need to memorize this list, but I want you to see it. Recognize these two things, that a stronger weak acid has a larger Ka, and that towards the bottom of this list are extremely weak acids. Okay. We do need to talk briefly about diprotic acids. So diprotic acids have 2 protons which can dissociate in aqueous solution. You've seen one of them, sulfuric acid, H2SO4. We list H2SO4 as a strong acid. And the first deprotonation is strong. So if we put H2SO4 in solution, it completely dissociates to form H plus and HSO4 minus. Okay. So that occurs completely. But the second deprotonation, where we take HSO4 minus, this is a weak acid. This does not occur to completion. So we're going to have our equilibrium arrows, and we're going to form H plus and SO4 2 minus. Okay. So while H2SO4 is a strong acid, HSO4 minus is a weak acid. That's sort of a special thing. There are other diprotic acids that I want you to be familiar with. Carbonic acid, chromic acid, and then phosphoric acid. Phosphoric acid is a triprotic acid, so it would eventually form PO4 minus. Okay. These diprotic acids, both deprotonations are weak. Okay, so what you're going to find with a diprotic acid, you're going to have 2 Kas. Usually we do Ka1 and Ka2. Okay. And Ka1 refers to the first deprotonation. So for carbonic acid, CO3, it's going to dissociate into H plus and HCO3 minus. Equilibrium arrows there, sorry. And this is going to have a Ka1 associated with that. And then HCO3 minus, it's going to form CO3 2 minus, and we're going to have Ka2 associated with that. And what you are going to find in every diprotic acid case is that Ka1, that first deprotonation, is going to be larger, stronger than Ka2. Ka1 greater than Ka2. So if we put a diprotic weak acid in solution, and we can write it in the general form, H2A. If we put this in solution, we will have HA, let's do it this way. We put H2A in solution, we're going to have HA minus and A2 minus in solution, and this is in order of decreasing concentration. So I think in my next slide I have a figure. So oxalic acid is another diprotic acid. It has a formula that is HOOC-COOH, which is kind of silly to write, but the structure looks like this. It's got 2 carbonyl groups, 2 alcohol groups. Okay. So that's oxalic acid. And you'll see I have Ka values written at the top here. Ka1 is 5.6 times 10 to the minus 2. And Ka2 is smaller at 5.1 times 10 to the minus 5. So if we put approximately 55 molecules, I don't know why I went with 55 molecules of oxalic acid in a container, all right, and we let them dissociate. Numerically, what we would find is 50 undeprotonated or completely protonated oxalic acids, so no dissociation has happened. Okay, the purple sphere representing most of the oxalic acid, all of that conjugate base, and the white sphere is representing the 2 protons. Okay. We would find that we would have about 5 molecules of the first deprotonated form, HA minus, and 1/10 of 1 molecule would be completely dissociated. So I know we can't really have 1/10 of a molecule, but if we're looking at even just these types of numbers, molecules on this scale, 55 different molecules, we wouldn't even get 1 molecule of the second deprotonated form. So what I'm trying to show you is that deprotonation occurs to a very small extent, especially with Ka2 for our weak acid. And these are relatively large Ka values, times 10 to the minus 2 and times 10 to the minus 5. Okay, so just to sort of summarize what we've talked about so far with weak acids, we put a weak acid in solution, it's going to react with water, and it's going to form the conjugate base, which we typically will write as A minus, and it's going to form hydronium ion H3O plus or H plus if we want the shorter form of writing that. Okay. So weak bases, we haven't really written out a general formula, but they behave the same way, except they start as bases. And so I like to write a general form for a base as B. So we'll have our general base equilibrium in water. So we'll start with our base B. And put it in water. Allow the equilibrium to happen. We recall that a base accepts a proton by the Bronsted-Lowry definition. And so we form the conjugate acid BH plus and OH minus. Okay. So if we look at where this is all coming from, we have our base. Water is going to donate a proton to the base, and that's going to bring along that positive charge, so BH plus. And then we're also going to be left with OH minus. Okay. So because we're working with equilibria, we need to, if we want to figure out equilibrium concentrations or pH, we're going to need to use ice tables. This goes back to what we were learning about in chapter 15. So we can write, practice writing our equilibrium, or our, acid ionization constants, or, the equilibrium constant K, and then because it's an acid, we'll call it Ka. So I have written out the formula for the equation for HF in water. So HF is a weak acid. And so when we write the Ka for this, we do concentration of products over concentration of reactants, just like we did in chapter 15. So for this specific acid, we would have concentration of F minus over concentration of H3O plus divided by the concentration of HF. And of course, we leave water out of this because it's a pure liquid. Okay, and as I've mentioned probably a few times now, I prefer to use our general acid, weak acid equilibrium. So instead of HF, HA. And the Ka for this follows the same pattern. Concentration of A minus times concentration of H3O plus divided by HA. Okay. And again, I like using the HA because it makes every weak acid that we deal with look exactly the same, which sort of reduces some of that cognitive load. Questions so far? Okay. All right. For weak bases, again, we can write a Kb value, so the base ionization constant, or the equilibrium constant for a base. We'll call that Kb. Now, as you see, this is a molecule called urea. Okay, that is a big, long formula that is annoying to write out. So I'm going to use the general base form. So urea is going to be reduced down to the letter B. So if we put this in equilibrium with water, we'll form BH plus and OH minus. As you can see, let's look at the formula here of urea. NH2, NH2CONH2. When it reacts with water, we add a proton. So now we have HNH2CONH2 and add that +1. Okay. So that is essentially the same thing as writing BH+. I just want you to see that they are equivalent. We're just saying that all of this is B. Okay? Does that make sense? So if we write out the base ionization constant, we'll have concentration of BH plus times concentration of OH minus divided by the concentration of B. And you'll notice that this has a really small Kb value, 1.5 times 10 to the minus 14. Kind of interesting. Very little of that urea is going to react to form the conjugate acid. Okay. Everyone okay with writing Kb's for a weak base? Okay. So let's actually do a calculation of the concentration of a weak acid in solution. So what this question is going to ask first is, what is the concentration of conjugate base in a 0.1 molar solution of acetic acid? And we're given the Ka value. I also want to find the pH. So what is the pH? Okay. One thing to note, I think with your homework, it often doesn't tell you the Ka value in the problem. If you don't have that, you can look that up. There's a table, and I think there's a link within the homework to find those values. You'll often need them in order to solve the problem. Okay. So just for the sake of doing this how I prefer, we're going to do HA plus H2O in equilibrium with A minus and H3O plus. Okay. All right, so this is now just like any other equilibrium problem that we've done, right? It says that we have a 0.1 molar solution of acetic acid. That's an initial concentration of acetic acid, okay? That sort of has to be implied in the problem. We don't know any equilibrium concentrations. We know what we put into solution. So we have 0.1 molar, and again, remember to use concentration in your ice tables. So 0.1 molar HA. We're not going to worry about water, so pure liquid. Okay. We don't know, there's no initial concentrations of conjugate base, A minus or H3O plus in these solutions. So we're going to have 0 in our initial lines for A minus and H3O plus. So what we want to determine now is at equilibrium, what is the concentration of A minus? And what is the concentration of H3O plus? Okay. We want to know the concentration of conjugate base based on what the question itself is asking, and then from H3O plus we can get the pH. Okay. So we're going to have minus X in our change line for the HA, plus X for A minus, and for H3O plus. So then at equilibrium, we're going to have 0.1 minus X for HA, X moles per liter of A minus, and H3O plus. All right, everyone okay with that? Okay. So now we can plug these values into our acid equilibrium constant, Ka. We're told that that value is 1.7 times 10 to the minus 5. Again, this is going to be equal to the concentration of products over the concentration of reactants at equilibrium. So we'll have x times x divided by 0.1 minus x. So if we multiply this out and rearrange it, we're going to end up with an equation that is minus x squared minus 1.7 times 10 to the minus 5x plus 1.7 times 10 to the minus 6 equals 0. So setting everything equal to 0 because we're going to have a quadratic. Okay. So how did I get here? I took what's in the denominator on the right-hand side, multiplied both sides of the equation by that, and rearranged from there. Okay. Okay, so we could solve the quadratic here. If you don't recall, solving for x with the quadratic, we use minus b plus or minus the square root of b squared minus 4ac divided by 2a, where a is the value that's in front of the x squared, b is what's in front of the x, and c is the other piece. I will let you work that out at some other point. I'm going to give you the answers here. We end up with x is either 1.3 times 10 to the minus 3 or minus 1.3 times 10 to the minus 3. Okay, so those are the two answers to solving that quadratic. Which is the correct one? It's got to be the positive one, right? Because we know that at equilibrium, the concentration of A minus and the concentration of H3O plus is simply X, okay? So X cannot be a negative. And so X is going to be 1.3 times 10 to the minus 3, which is equal to the concentration of acetate ion, which is also equal to the concentration of H3O plus. Okay. So we've answered the first question, which is what is the concentration of conjugate base? By going through the ICE table, solving the quadratic, we get 1.3 times 10 to the minus 3 molar. For solving for the pH, we need to take minus the log of the H plus or H3O plus concentration, which is also 1.3 times 10 to the minus 3. And again, I'm getting that because both A minus and H3O plus are X in the equilibrium line in my ICE table. And so we take minus the log of that, we'll get 2.89. Okay. Questions? Yeah. We found, we found the pH of the solution, of the
just of the whole solution.
Yes, because the acid has one proton. So whenever we have a monoprotic acid, an HA, not an H2A, not diprotic, we're going to end up with the concentration of the conjugate and the concentration of H plus are equal because of the stoichiometry. So we use the same numerical value as the conjugate base. It's just that it's also the concentration of H plus, or H3O plus. Y'all remember doing the concentration or the pH of a 0.1 molar HCl solution? So remember, HCl is a strong acid. We wanted to calculate the pH of that. We know that completely dissociates. pH is equal to minus the log of 0.1. I don't know why I did that. That's going to give us a pH of 1. Okay, just for comparison here, pH of a strong acid of 0.1 with a concentration of 0.1 molar is 1. We have a weak acid. Now the concentration of that same concentration. Let me see. The concentration of a weak acid, the pH of a weak acid that is the same concentration of a strong is much higher. And that's because there's less dissociation. There's less formation of H+. Okay? And if we did a pH of phenol, which had a something times 10 to the minus 10 Ka, it's going to be even higher than 2.89. Okay. Any other things from what you're seeing right now? All right. So remember on the practice test, there was this assumption business, right? How do we get away from using the quadratic? What we can do is, once we're at this point, we can make assumptions that make these problems easier to solve, sometimes not always. Okay, so let's go through that. I'm going to open up another slide here like this. Okay, so we have our weak acid. We did some math. We started with a 0.1 molar. Now we have Ka equals 1.7 times 10 to the minus 5. So I'm basically just reworking that same problem. And we'll see if we can make an assumption here to get rid of the need to solve the quadratic formula. So I can't remember how the video described doing the assumption. So I'm going to show you the way that I do it, and it will work for you. Okay. Okay. And we need to also remember we had 0.1 molar acetic acid. So the assumption is that if the initial concentration of HA, so the 0.1 molar in this case, divided by the Ka is greater than 1,000, then you can get rid of X. So we'll do that again. If the initial concentration of the weak acid, so HA is 0, divided by its Ka value is greater than 1,000, then we can ignore X, but only the one that's relative to the initial concentration. Okay? So that means only the one that is showing up here. Okay? We'll never be able to ignore the X squared. It's going to have to be the one that is being added or subtracted to another value. Because essentially what this is doing is saying, well, this X is going to be so small compared to this value that if we subtract it, it doesn't make a difference to this number. Okay? Everyone okay with that? So it's as easy as taking our 0.1 molar divided by the Ka, which was 1.7 times 10 to the minus 5. What do we get? I didn't write it out. It's greater than 1,000. Yeah? Check. So what we can do then, back in our Ka expression, oops, this will become 1.7 times 10 to the minus 5 equals x squared divided by 0.1. So we're getting rid of that x in the denominator, in the parentheses. Okay. Now this is a bit easier of a problem to solve. We will have 1.7 times 10 to the minus 6 equals x squared, and we can take the square root of both sides and get our answer, and we should get 1.3 times 10 to the minus 3. Which is the same thing as what we got on the previous slide. I can't recall also what your book uses as something. If it's not this, I'm sorry. But this will work for you. Okay? I think it's the easiest way to think about it. You already know going into the problem what your initial concentration is and what your Ka value is. So right away you can figure out if you're going to need to watch that. Questions on that? Okay. We're going to do one more type of calculation with that acetic acid problem that we just did. And that is looking at the percent ionization. Okay. So sometimes we want to know what are the percent of molecules that have ionized, right? And if we're looking at a weak acid, the percent of molecules that react to give ions, so the ions are going to be A minus in this case. If we're working with a base, the ions that are formed are BH plus. Okay. Percent ionization might look familiar to you. It's very similar to percent yield. Okay. So we essentially have in our percent ionization equation the concentration of ions formed. So this is an equilibrium value over the initial concentration of weak acid or weak base. Okay? In this case, weak acid. So for our acetic acid problem that we've been working with, the concentration of A minus that was formed is 1.3 times 10 to the minus 3. Our initial concentration of acid was 0.1. Multiply by 100 to get a percent, and we'll get 1.3%. If we wanted to find the percent ionization for a base, we would have the concentration of BH plus at equilibrium divided by that initial concentration of base times 100 to get the percent. Just one more way of showing what's happening in a weak acid or a weak base problem. Okay. So let's work on this problem, all right? Here we're going to take a different acid, acetyl salicylic acid. We're going to take 0.018 moles of that and dissolve it in 0.54 liters. Because I'm feeling nice, I will give you the concentration of that, so dividing the moles by the liters to get 0.0036 moles per liter. Okay. I want you to find the pH of that solution. Check your assumption on this one, and it's going to fail. Okay. So I want you to see, this one you will have to use the quadratic, but I want you to practice using the assumption and see that it does. Okay? Work with your neighbors on this one. Yes. Did I just divide by 0.5? Did anyone else get 0.0033? Is that right? Sorry, my mistake. I was being nice and then failed you. Huh. One zero. What have I done? Oh. Oh, I did it wrong. Yeah, no, there we go. Okay, sorry, I made a correction, y'all. My apologies. 0.033 concentration. Should make sure this still fails then. All right, how's this going? So I have the mistake like all the way through my calculations in my notes, so I'm going to need your answers. So hopefully we've done it correctly. So we want to find the pH of the solution. pH is always at equilibrium. Okay? We always need the H3O plus concentration at equilibrium to find the pH. So our initial concentration of HA is 0.033. Not going to worry about water. Initial concentrations of A minus and H3O plus are both 0. We'll have minus X for HA, plus X for A minus and H3O plus. Ka is 3.3 times 10 to the minus 4. So we'll have x squared over 0.033 minus x. We can check whether we can get rid of this x relative to the 0.033. So we can check that our assumption will work, and it won't. So what we've got is our initial concentration of acid, 0.033, divided by the Ka, 3.3 times 10 to the minus 4, which is about equal to 100. So it's less than 1,000, meaning we can't assume that X is small relative to 0.033. Everyone agree on that? Okay. So we need to leave it in and solve for the quadratic. What did we get for X? Let me do that. I can't. What did we get? Yeah. 0.00316. Everyone agree? Close-ish? What'd you get? 314. Okay. Yep. I'll take both. They sound good. So if we look at what we have inside here, if we were to not have subtracted 0.00314, we would be within this digit of significance, which is why we can't ignore that X value. Okay. Okay, so those are going to be the concentrations of A minus and H3O plus. We'll do or, one of those. So what do we get then for pH? 2.5? Good enough. Cool. Awesome. Okay, so there's an example of how you can't get rid of the X value. If we want to look at percent ionization for this acid, we're going to take the concentration of A minus, 0.00316, divided by that initial concentration, 0.033. And we'll end up with a value times 100. I can do that one. I'm not doing the quadratic on my phone. Sorry. Honestly, I'm not doing it most times. I get 9.58%. Is that right? Y'all, did I do it right? Okay. Cool. So you can see based on this percent ionization that this is a stronger acid than the acetic acid. We have a greater percent ionization here, almost 10% compared to almost 1%.